It is a great pleasure, indeed an honor for me to be here at the inauguration of the center named after such a legendary person in physics. I'm sure that Hans Bethe would have loved to see the present state of physics, where astrophysics and particle physics are joining forces to try to understand the universe of large things and the universe of small things. And we are about to enter a new period where exciting experiments will be done with the LHC, the Large Hadron Collider. In fact, the Large Hadron Collider will, in some sense, only make a modest step forward. This is the way I like to view nature, physics, as a highway towards smaller and smaller distances and higher energies. And well, today we are only about here, and you see at the right of this, oh yes, this is a, okay, thank you. So here at the right, here, by the way, you see the distance scale, the typical distance scale relevant, and all these numbers are steps forward by a factor 1,000. So you see many factors of 1,000 are needed to go along this highway. The energy goes up with similar factors 1,000 here. Now here you see all these symbols which indicate all the particles that have been discovered at this typical distance range and energy scale, and that the particles stop right here. There are no particles beyond that scale. Now, this is also the point at which experiments could be done. So you might as well suspect that this list is not going to stop at all. There will be many more particles out here, but we haven't seen them because no experiments could be done in that domain. However, there are competing theories and ideas that maybe this entire region is empty. We don't see things, we don't have any things there because we can't see them, but also because they aren't there. And so this may be a desert, a highway through a region with nothing at the side, and then eventually you might think that you go to infinity, but actually there's a very interesting scale high up, way out there, with the letter GUT, Grand Unified Theories. When we extrapolate today's understanding of the standard model, which describes nature in this domain, we can simply extrapolate mathematically. Close our eyes, assume that nothing strange happens out here, and just extend what we think we know. And then, roughly in this domain, forces which are entirely different here, the strong, the weak, and the electromagnetic force, they all seem to obtain equal strength in this domain, and that's a reason to suspect that maybe there's a fundamental new kind of unification taking place. At the very, very short distances, all these forces are equal in strength. Maybe that's because they are just one particular force out there. Not far from that domain, actually very close, is a region where we write down quantum gravity, the so-called Planck length, and I'll explain in a minute what that is. The LHC only makes a step which looks small on this picture, but actually it's a factor 10 or more in order of magnitude of the energy resolution that we can make, and so also the distance resolution. So we expect many new particles to be discovered here, perhaps, and the machine hasn't really been turned on to its required energy, so it's designed energy, so we don't know as yet what this machine will bring. Now you might wonder, why is gravity, the gravitational force, so much more difficult to handle than other forces in nature? Because typically the force law of electric and magnetic forces is that the force is a constant times the product of two charges divided by their distance. And that's the force by which two charges either repel or attract. And in the case of gravity, it's just the same way. In the case of gravity also, we have a constant times two things here in the numerator, and then divided by the distance squares. These distant things in the numerator are the masses of the particles. So why is it that having masses here rather than charges makes a force so different? At first sight, you would say, well, they're both a 1/r² force. So if you can handle one, you can probably also handle the other. Well, there are subtle differences, and I'll mention them one by one. In fact, you can describe both forces when you do quantum field theory, you can subject both forces to quantum mechanics. And as long as these forces are weak, we understand what we have to do. In the case of electromagnetism, the exchange particle is a photon. And that is a particle with spin 1. And in the case of gravity, it's a graviton. And that's an object with spin 2. So, mathematically, when you try to figure out everything and you look at the space-time behavior of these forces, you find that the major difference between the photon and the graviton is their spin. But what is it that makes spin 2 so much more difficult to handle than spin 1? And there's another little difference in forces, which I also will explain more later, that in the case of electromagnetism, like charges repel, opposite charges attract. In the case of gravity, that's the other way around. If you have two masses which are equal in all respects, they attract each other, they don't repel. In fact, that is directly linked to the fact that the exchange particle has even spin, whereas here the exchange particle has odd spin. In fact, there's another force known where the particle being exchanged has spin 0. That's the nuclear force between protons and neutrons. And indeed, protons and neutrons, whether they are alike or different, they're all being attracted into the atomic nucleus. So like things, again, attract there. And that's because the exchange particle then has spin 0. They're not being attracted to exactly one point in the nucleus, and that's because the rho meson, which is heavier than the pion, will then also be exchanged, and that causes a repulsion. So then things become more complicated. And that's how the nucleus obtains its shape. But in the case of gravity, again, like things attract. And I'll return to that in a minute. Now, of course, we all know, we have heard about Einstein's ideas about gravity. Einstein discovered that gravity could be related to the fact that space and time are not described by a flat space, but by a space with curvature. And it's actually space and time which are curved. Not this is a picture, an artist's impression of a curved space. But actually time is also curved, and that is expressed by saying that if you have a clock far away from, say, the Earth or another heavy object, and a clock close to that heavy object, the clock closer by goes slower than a clock far away. And if you now draw a closed circle in space and time, you would find that that is a way of describing curvature, but now in the space-time sense. That was Einstein's great discovery. If you do all this right, you get a unique theory of gravity, which has as its only possible extension would be a cosmological constant, about which there's much to do today, but at small distance scales, the cosmological constant appears to be 0, and so gravity, Einstein's gravity seems to be a unique theory. So unique that you can take this field as it is, write down its equations, and subject that to quantum mechanics. As long as the field is weak, you know exactly what to do, and you find that the energy quantum of this thing will have spin 2. Now let me try to explain in words why the graviton has spin 2. Many of us can do that in formulas. We can observe that gravity is described by a tensor field, and that has two indices, and the way it behaves under rotation gives it a spin 2 representation of space and time. Well, I would like to give the physical argument. The physical argument is rather neat and can be explained in terms of totally classical features of gravity. Here is the Earth, and planet Earth has a gravitational field around it, but also the planet Earth is affected by its moon. And let's suppose the moon is there, and the moon attracts the water on the Earth. And now you know about the tides, that water which is in, between the Earth and the moon is attracted in the direction of the moon. And that's because the water here is a little bit closer to the moon than the water there, and because it's closer, it's being attracted towards the moon. Now, why is there a bulge here? That's because actually Earth and Moon, the Earth is not standing still while the Moon goes around it. Earth and Moon actually rotate about a common center of gravity, which is actually a point inside the Earth, which some say here. And for that reason, this region here is undergoing a centripetal force. And so for that reason, this water here is being dragged or being swept away to outer space again. It's too far away from the moon. The moon is attracting this region weaker than it ought to because its average force cancels out in the center of the Earth. So there's a bulge here as well. So while the Earth rotates in 24 hours, you have twice high tide and low tide. And this, of course, is a fairly well-known feature of classical gravity, and anybody can understand that if you think a little bit about it. Now, suppose that the moon rotates around the Earth. Now, actually, of course, the Earth rotates underneath the moon, but let's consider the moon at different positions with respect to the Earth. Then you find that this bulge will rotate with the moon. And now you see something remarkable. If the moon makes a rotation of only 180 degrees around the Earth, then the bulge looks the same as before, right? So here it looks the same. And by the way, the sun also contributes, but the sun is further away, and therefore its effect is somewhat weaker. It's mainly the moon which causes the tides. Now, you can notice now that if you follow the moon over an angle of 360 degrees around the Earth, you find 2 maxima and 2 minima. This now you could compare with a wave function of something with angular momentum, and you find 2 peaks and 2 valleys in the wave function. Whereas if this were electromagnetism, then if you would have a plus charge and a minus charge here, then the polarization would be in this direction if the source would be here, in the opposite direction if the source were there. So if this were electromagnetism, there would be only 1 peak and 1 valley if you go around 360 degrees. This is an angular wave function, and therefore it has to do with angular momentum. And well, then the exchange field, well, it depends on the position of the moon. That would be compared to orbital angular momentum. But this intrinsic feature of the bulge, rotating twice when you go around, is some internal feature of gravity. And that then translates into an internal feature of the graviton, the particle that transmits the gravitational force. And that is the reason why the graviton has spin 2. Well, it's not the real reason. The real reason is mathematics, but this is the same argument in words. So this is the argument in words why the graviton has spin 2. If you don't believe it, well, then I have to refer to the real calculations, which is too complicated to explain here in detail. Anyway, now the other thing about gravity, why they're both, gravity and electromagnetism are both the 1/r² force. Why is it so different anyway? Well, mass is also energy. As Einstein told us, mc² is energy. If you go to the highly relativistic case where particles get mass because they have intrinsic mass, but they get much more mass because they have energy, then if I accelerate particles to way beyond the non-relativistic case, highly relativistic velocities, then they enormously gain in mass. And at the same time, mass represents, for relativistic particles, the mass is roughly E/c², and E is closely related to momentum, h/c. And so what you get here is h/c divided by the wavelength of the wave of the particle. In other words, the numerator in this law here has also a 1/a wavelength in it. So that you can also compare to the distance between the 2 objects. And so you get 2 other factors r in the denominator. So it's not really a 1/r² force. But when you go into the highly relativistic domain, it's going to be 1/r to the 4th force. And that means that when r is very small, this force will increase much more rapidly in strength than ordinary electric and magnetic forces, where the charges q are distance independent. They are, in fact, dimensionless numbers. So in the usual units of nature. So gravity will gain in strength relative to the other forces when you go to smaller distances. Now, gravity, under ordinary circumstances in particle physics, is an extremely weak force. You might think that gravity is the strongest force that you feel because you have to, whenever you stand up from your seat, you have to fight against gravity and not electromagnetism or let alone the weak and other forces. But that's only appearances. The reason why gravity feels to be such a strong force to you is that there are many billions of atoms in your body, and there are much more trillions of atoms in the Earth, and they all pull in the same direction. So all objects that gravitate in the same sense, and they reinforce each other. Whereas in the case of electromagnetism, there are as many positive charges and negative charges in your body. So they tend to neutralize each other. Also in the Earth, electric and magnetic forces neutralize each other because there are as many positive charges as negative charges. So that makes that the electromagnetic force in the Earth balances out to 0. Nevertheless, when you stand on the floor, there's only one layer of molecules in your shoes, and there's one layer of molecules on the floor here, which is sufficient to counteract all that. And even those molecules have as many positive and negative charges in them, but just as very slight residual force, which is sufficient to be stronger than all these billions of atoms that are trying to pull you in the same direction downwards. So you see that electromagnetism is, in that respect, a much stronger force than gravity. Electromagnetic forces are felt for individual particles, but when you calculate what's the gravitational force by which individual elementary particles attract each other, that force is so tremendously much smaller than the other forces that you can never find or detect such a force in ordinary experiments. So you can't. You have to wait until gravity becomes strong. When will that happen? Well, that is the easiest calculation you can do. You can even show that in a colloquium, and that is that you take the three fundamental constants of nature. You take Planck's constant, you usually divide that by 2 pi. You take Newton's constant, you might divide that also by 8 pi or something like that if you want, but usually take it this way. And you take the velocity of light. You have 3 fundamental constants of nature. And they're all expressed in kilograms, meters, and seconds in certain combinations. These are the dimensions, the units of these forces. But they each carry kilograms and seconds in a different combination. For instance, the velocity of light is just meters per second. Now, that means that if you take certain combinations of these constants, you get so-called Planck units. And what you have to do is you take, for instance, the square root of h bar times g divided by c to the third. Then if you look at the units, you get something in the dimension of a length that you can express in centimeters, and that's 10 to the minus 33 centimeters. Another combination has a unit of mass, this combination, and this combination, if you divide by another factor c, you get something with a dimension of a time. So there's a fundamental unit of length, of mass, of time. In fact, all fundamental units of nature are then fixed, so all numbers in nature will become dimensionless if you use those 3 constants of nature. Now, the constant of length that you get, 10 to the minus 33 centimeters, well, that's a small distance. But if you look more carefully, you find it's a very small distance. It's much, much smaller than anything we do in particle physics, which usually is something of the order of 10 to the minus 15 centimeters or something. So you see that at least 18 orders of magnitude are still missing to go there. So that is indeed a very small length scale. This mass is very interesting because this mass, 20 microgram, could be a very useful unit of mass in physics. The reason why it's not used as a unit of mass in physics is that Newton's constant g is actually very poorly known, only 1 part per thousand or so. And that's because gravitational forces are very difficult to measure very precisely, and that is because everything gravitates. So when you do an experiment, you get disturbances from everywhere, and so it's hard to do the calculation, the measurement very, very accurately. So it's already a big achievement that people could measure g to better than 1 part per thousand. But most masses can be measured much, much better than that. And we don't know this number accurately enough. And so all these numbers are not known very accurately. And therefore, they're not used as fundamental units of nature. But they could have been. The time scale is ridiculously short. If anybody wants to tell you a computer saying that it does calculations faster than 1 in 10 to the minus 44 seconds, don't believe him, because generally people think this is the shortest time scale possible in nature. Anyway, now about the repulsion and attraction. Electromagnetism, like charges repel, opposite charges attract. In the case of gravity, that's the other way around. Like things attract. But when you have that situation, you can imagine there's something to worry about. If like things attract, they tend to accumulate and repel the other guys, which are different. So like things attract, then they become stronger, the source of attraction becomes bigger, so those things that attract other like things even more strongly. And then they become bigger again, they attract other things stronger again. That smells like an instability of nature, so you might get an implosion or something when you get lots and lots of matter. And that's what's called a black hole, eventually. Of course, planets and stars are also the result of this attraction becoming quantitative when you have lots and lots and lots of atoms and molecules together. But you can go on like that, and then something very bad happens. Now, I probably don't have to say that in this audience, but some physicists suspect that black holes don't exist and that they are unreal. They are just an extrapolation of known laws of physics beyond their realm of validity. That's what some people claim, but I have fairly simple arguments to say that's very unlikely. Because only using the principle of general relativity, saying that acceleration and gravitation forces are the same thing, that's really all you need to say to prove that black holes actually must exist. And to demonstrate that black holes must exist, I'll now show to you how to make one out of ordinary matter. So we don't need any exotic form of matter to make black holes. A star forming a black hole doesn't have to go through an exotic phase. It might, but it doesn't have to. It can go through an ordinary phase. So to highlight that, I'll make a black hole for you out of mobile phones. Mobile phones still working while they make a black hole. All these are mobile phones. The only catch is you need very many of them. You need about the mass of a galaxy or so. And you put them in a spherical configuration about the size of a light year or something like that. And then I put them in a spherical configuration, and I make sure that they don't touch each other. So nothing on Earth stops them from properly working. As long as they are charged, they'll function. And like a mobile phone, you can use them while they do all this. And this also does not have to be very accurate. Another objection people sometimes raised against black hole theory is that it's an idealization of a perfect laws of nature. If you make a small perturbation, it won't happen anymore. No, if you make a 10% error in here, it's still fine. The argument will still work. The argument is that if you calculate the gravitational field generated by these mobile phones, you find that within this sphere, this spherical configuration, there's practically no gravitational field left. And that's because these are still non-relativistic. They're standing still. So the same laws apply as Faraday's argument, saying that inside a conducting sphere, even if you have a charge on the sphere, inside the sphere there will be no relic electric field around. For the same reason, there's no appreciable gravitational field inside the sphere. Outside the sphere there will be. It will be fairly weak, but I made these things light years across, so it will range very far. And that implies that still, because the field ranges so far, the gravitational potential is very deep. But so these phones will then start to attract each other. They'll come closer to the origin. And because the thing shrinks because of gravitational forces, the field here becomes stronger. And also the gravitational potential in which they'll all sit will become deeper. And at some point, a magical line will be crossed, which is very easy to calculate. And that's the line where the gravitational potential of every mobile phone becomes equal to its own mass energy. So that means that in order to escape from this line, the mobile phone would have to be given the speed of light. Now, if two mobile phones collide at the speed of light, they will both basically explode and nothing will be left. So they certainly won't continue to function. But these mobile phones will then, with respect to their neighbors, their velocity will always be very small. So occasionally two of these things collide, but they won't collide any worse than like this. So they might still function after that collision. And if they do things sufficiently carefully, nothing has to collide with big force, so they'll all still function. You can still call them. Except when they cross that line, you will no longer get the signal back, because the signal back would have to go faster than light, and that's impossible. So that's the only catch, but that's something to worry about for someone very far away, that you can't reach them anymore, or at least you can reach them, but you can't get your answer back. But locally, there's nothing wrong with local laws of nature, and all you need to understand as far as matter goes is you have to understand how mobile phones work, and there's no big mystery there. So they'll cross that line, but now something happens that's more worrying. They'll start to occupy a smaller and smaller space because they all attach each other, and the attachment becomes stronger and stronger. Now they'll touch each other, and some will break inevitably, and only after a short moment they'll all break, because they'll all be squeezed in such a small volume that they'll melt, they'll undergo chemical reaction, they'll undergo nuclear reactions, they'll become a plasma, and certainly won't function as mobile phones anymore. But still you can apply the physics of chemistry, the nuclear physics, plasma physics, you can apply elementary particle physics for a while, quantum chromodynamics, but then, well, then they all reach a point in the center, and now all known laws of physics become dubious. Right now you don't know for sure anymore what happens. It's also totally irrelevant what happens inside, because we can't see it from if we stay outside this object itself. The only thing we see is what happened when these mobile phones crossed this boundary here, and that's ordinary physics. In other words, this argument shows that the argument that black holes can be formed is one that applies ordinary physics with only this one line of Einstein there, that acceleration in gravity is the same thing, and that's really all you need to understand how to make black holes, and even light from there cannot escape. So doing that, you can ask, why are black holes so difficult to study, and what problems do they give rise to? Of course, it's nice to go a little bit back in history. Karl Schwarzschild needed only a couple of months after Einstein published his theory of general relativity to realize, he was a good astronomer, he said, look, these equations that Einstein wrote down, I can solve them, at least for the spherically symmetric situation. And he wrote that down, and this was his solution. Not quite the way he wrote it, but the way we write it in modern notation, but it was a solution that he found. He solved the equation correctly, but where capital M is actually a combination of Newton's constant times the fundamental mass, as would be measured by someone sitting at a great distance from this configuration. I won't bother you with all the details of this formula, except, of course, point out something peculiar about it, and which worried Schwarzschild a great deal. When he found the solution, he said, look, there's a 1 minus 2m over r here. If r becomes equal to 2m, where this m was just a constant of his equation, then the denominator here explodes, or becomes 0, and so this expression here explodes, and here also something funny happens. So how do we deal with that? Schwarzschild did not understand that this actually was a coordinate singularity that you can get rid of. So he thought this is a physical problem, and therefore he redefined his coordinate, his distance coordinate, such that this happens at the origin of his space. And then he thought that he cured the situation. That was the wrong cure, as we now know. But unfortunately, Schwarzschild died a few months after he did this publication. And so he never witnessed what happened next. But what happened next is we look at this singularity in more detail. That's dr, that's an infinitesimal displacement divided by 1 minus 2m over r. Well, if you write dr over the square root of r minus 2m, that's just basically the square root of this, including its singularity at r equals to m, and you rewrite that as d rho, then that's a trivial thing to integrate. You find that rho is plus or minus 2 square root of r minus 2m, or rho squared is r minus 2m. So all you have to say is introduce a new coordinate rho, which is such that its square is r minus 2m. And then the singularity here disappears. You get, okay, a smoother behavior of rho with no singularity anymore. The funny thing about this, this observation is the switch of the sign. Now you have rho squared as this, so when rho is 0, this solution is glued continuously on the solution where rho is negative. But the r has the same value as before. So this looks like this space and time is doubling up. For every r, there are 2 rhos. So you have actually a space which is twice as big. I'll return to that in a minute, but first let me concentrate for a moment on this other peculiarity, which is here there's also a 1 minus 2m over r. That quantity becomes 0 if I goes to 2m. And that's equally strange. It means that essentially the effect of a time change isn't seen in the solution anymore. In modern terminology, we know that a local observer will not observe any time there. Well, for that local observer, time will stand still. So it is a point in this configuration where time stands still. I told you that clocks go slower when you come closer to the Earth. Well, clocks will stand still altogether at this point where r equals to m. Of course, that r equals to m is the horizon, is that dotted line, which I had before, is the point where crazy things happen. And graphically, we can express the situation as follows. The universe gets curved because of general relativity, like this thing. I take one universe, I take another universe with a similar curvature, and then in a sense, a black hole is something like this. It's a wormhole which connects one universe to another universe in a smooth way. And so there's one universe here, and this is, of course, a black hole. And the question now is the black hole perhaps a wormhole? Well, for one thing, there's the line where, or the seam where you seam these things together. Actually, of course, space and time is more dimensions than just the two which I draw here, so you must see this as a surface rather than a line. But at that line, at that surface where these two universes are stitched together, time stands still. So a traveler cannot actually go through it because then he needs time to proceed as he goes through this line. So there is something funny, something that has to be studied a bit more about this horizon. And because of that, actually, you can't really connect to our own universe, but you connect to a universe where time is altogether different from our universe. How exactly? Well, you don't know. Mathematicians understand that actually, since I didn't say in what kind of space this whole thing is embedded, this other universe can be anywhere. It could be our universe, it could be another universe. We don't know. Anything is possible from a mathematical point of view. Anyway, this gave rise to lots of speculation about what black holes really are. Are they wormholes to other universe or not? This is something one has to investigate much more during physics. But you cannot really travel from one universe to another. And one thing is, of course, that you have to go through this dangerous wormhole. There are science fiction addicts often dream of making wormholes to travel to other parts of the universe, but they forget quite a few practical difficulties when they try to arrange such a thing. One thing is that the only wormhole that you could get through without being torn to pieces by gravitational forces would be a wormhole 1,000 times heavier than the sun. And if you would have a lighter wormhole, a lighter black hole, like, say, the mass of Jupiter, you would be completely torn to pieces. This hole would only be 3 meters in size for Jupiter, but at different size, the velocity differences would be of the order of the speed of light. So being yourself, say, a meter or so across, if you sit in a tiny space, you would still be torn to pieces if you try to go through such a black hole. So there are all sorts of practical difficulties in that respect. Now, this horizon is something very peculiar. If you think of an astronaut going to a black hole, a very large black hole, then the astronaut, seen from distance, it would seem that the astronaut stops just before the black hole, just before the horizon. And the reason why he stops, as we've seen from the outside world, is that light takes an infinite amount of time to get out. So the closer it comes to the horizon, the longer it takes for light to come out. So we actually don't ever see him cross the horizon. Whereas the astronaut himself will simply think that he goes right through. As if he is able to survive that, locally speaking, you would think that he goes right through the horizon. This means that observers have a fundamental difference of opinion about how to interpret time. So the astronaut himself will think time has to be measured this way. The astronaut seen from a distance has time go to infinity before it actually goes through the horizon. So the notion of time is fundamentally different for the two observers. And the consequence of that is that they also experience the notion of particles very different. And that was a big discovery, essentially made by Stephen Hawking, that black holes do something very strange with elementary particles. And that's if you try to apply quantum field theory, something strange with particles happen. There's a story with this picture. These are 3 movie stars, one playing Einstein, one playing Newton, but Stephen Hawking playing Stephen Hawking. This is an episode in Star Trek. And I can say something more about it, but I want to continue my story about black holes. So Stephen Hawking made a big discovery. Because of this disagreement about what particles mean, if the observer goes through into the black hole, says that he is surrounded by a decent-looking space with only a couple of particles, but certainly not an infinity of particles around him, just a few of them, then the observer who stays outside we'll have to conclude that that black hole emits particles forever. And so this black hole emits particles at a constant rate. And that's the consequence of this quantum field theoretical argument. It's very interesting because this turns black holes into something which one might study from the point of view of particle physics. A black hole is not a divine object that behaves totally different from any known form of matter. No, it is very Earth-like. It's like a bucket of water. If you put that in outer space, it will evaporate. Water molecules every now and then will detach and go into outer space. Well, similarly, a black hole, it loses matter in outer space, and that turns into something dynamical, something interesting that you can study physically. That holds for large black holes, but when they become very, very small, this effect becomes much more important. And the very small black holes then become an interesting form of matter all by themselves. The tiniest black holes you can imagine would be black holes of the order of the Planck size. Those would emit particles like crazy, and they would possibly behave very much like elementary particles themselves. Now, these observations are now considered so important when you try to understand gravity, in particular at the Planck scale, that we say, well, you can't really understand gravity properly unless you also understand how black holes behave at the Planck scale. At first sight, you would think, well, the argument is all you need to know what the horizon does of the black hole, but I just explained to you that the horizon is described by ordinary laws of nature, nothing exotic. So why would it be so difficult to describe the horizon of a black hole? Well, hold on, because there is something very exotic and very strange about the horizon, in spite of what I just said. Let me just for a moment give you Hawking's argument, but now in a somewhat different setting. We can explain many ways why the black hole emits particles. And one nice physical interpretation, again, is that at this horizon, there are vacuum fluctuations taking place. Now, vacuum fluctuations normally mean that you have pair creation of particles, and then these particles annihilate again. Since the vacuum has the lowest possible energy, those particles which are formed by vacuum fluctuations cannot escape because they would have to represent energy, and that energy is not available in the vacuum. So the only thing those particles can do is go back to where they came from or find other particles from other vacuum fluctuations and annihilate as quickly as they were formed. So that means that in the vacuum, according to quantum field theory, there are fluctuations of particles being created every now and then, but the only thing they can do is go back and annihilate again. So that's what we call fluctuations, which have indirect effects to the physical properties of other particles in the vacuum, but it doesn't disturb the notion of vacuum itself. Now, however, consider the horizon of a black hole. A particle outside, when it escapes to infinity, it must have positive energy. A particle on the horizon, however, has so much gravitational energy that together with its mass energy, it is actually in a negative gravitational well. So if you add to that its own energy, you get zero. A particle inside the horizon actually, in a sense, can carry negative energy altogether. So now, if you have fluctuation of particles, one particle with positive energy can go out, and one particle with negative energy can go in, and then they don't need to annihilate each other anymore. So whenever vacuum fluctuations happen to take place at the horizon, at that moment, then one can go to infinity, the other can go to zero. The one which goes in cannot cross the horizon back out again. The one that goes out has enough energy to disappear into infinity. And that is a legal solution to the equations. So now you can see that at least from an energetic point of view, the black hole can emit particles, and Hawking computed it does. And he could compute the rate. The rate is as if the black hole carries a certain temperature, and it emits particles the same way as a light bulb emits photons when it is heated to a high temperature by an electric current. So just the same way the black hole emits particles. And the rate by which it emits particles is controlled by its temperature. And the temperature is such that the Wien wavelength is of the same order of magnitude as the horizon, the size of the black hole. So that's just a rule of thumb to compute this energy. This is basically the Wien wavelength, which is now proportional to the radius of the black hole, and it's inversely proportional to the temperature. So that means that the temperature is inversely proportional to the mass of the black hole. Now, if you now plug this into a calculation, you say while emitting particles, the black hole must lose energy. And while it loses energy, it must become smaller because its radius is proportional to its mass. If it loses energy, it loses mass, its radius becomes smaller, its temperature increases. Now, its surface area decreases. So you can say, okay, it emits more intense light, but over a smaller surface. Yes, but the surface goes like r squared, and the intensity of the light goes like t to the 4th power. So that is 1 over r to the 4th. The temperature wins. The intensity is r squared divided by r to the 4th. That's 1 over r squared. And therefore, the black hole, while it shrinks, intensifies its radiation altogether. So it becomes a more and more powerful radiator. It starts to radiate more and more. Eventually, an enormous amount of radiation is emitted in a split second. And then what happens? Well, then the black hole must somehow disappear into an explosion of some sort. In fact, you can calculate the intensity of such explosions. They should be visible from many light years difference. This is distance. This would be a tremendous explosion that the black hole would undergo. And when people first saw gamma rays, there was some hope by relativists such as Stephen Hawking that these were evidence of microscopic black holes exploding into nothing. But now we know that gamma rays, the gamma bursters, that they are actually distant quasars which which have a supernova explosion of some sort. And that has now been the explanation rather than this. But for a physicist doing particle physics, this whole feature gives you very interesting information about the very tiniest black holes imaginable. Now here I part from astronomy. Astronomers discuss very, very large black holes, but their Hawking radiation intensity will be negligible. Very large black holes have such a low Hawking temperature that's much lower than the ambient temperature in the universe. So large astronomical black holes always increase in mass. They don't decrease. Only the very tiny ones will decrease. But physicists cannot find any way in which to make these very tiny black holes. So even astronomers, they don't know how ever objects would collide with such an energy that they would make very tiny black holes, tiny enough for them to decay with Hawking radiation. Perhaps in the early universe, such tiny black holes were made. So not all hope is lost that such things exist, but it's going to be very difficult indeed to make them. However, when you do quantum mechanics, you know that everything that can be made in principle should at least play a part in a quantum theory. You can't leave it out. So in a quantum theory, we have to imagine everything that is legal according to the laws of nature. And tiny black holes are legal solutions of the laws of nature. So we must include them in our picture of very tiny particles at the Planck scale. Our theory will be incomplete without them. So, okay, maybe you won't be able to make them, but at least you want to have a theory that includes a proper description of those things if they were made by some higher intelligence, more intelligent than we are. If they would be made, we want to know how they behave. So we want to understand nature in a complete fashion. Well, there's one little Gedanken experiment one can do with black holes quite easily, and that is we can consider a black hole plus matter. And I don't know what my time situation is, but maybe I don't have much time left, so I'll use only a few, well, 10 or 15 minutes, and then, but in the meantime, I'll throw this into a black hole. And then the black hole will increase in size. Look, it increased a little bit because it gained that much mass. So a black hole plus matter will undergo a transition into one single heavier black hole. But now with Hawking radiation, we can calculate the thing in the other direction. We can calculate the probability that the black hole emits objects. Now, the rule is simple. It's thermal radiation, so it emits objects which are controlled by the Boltzmann factor. So the probability of emitting a key or a coin in the black hole, all you have to do is compute the Boltzmann factor associated with that, and then you got that probability. Admittedly, that probability is very small, but at least it's there in principle. So now we have a two-way process. It may emit alarm clocks as much as it absorbs them, and it will emit keys and coins as easily as it can absorb them. And all you have is the Boltzmann factors. So we have actually this process in two directions. We have some information about it. And that's interesting from a physical point of view. Let's compare the one process with the time reversal of the process. And then there's a little argument. I first give the argument in words and then in formulas. The words is that imagine the number of states a black hole can be in. Imagine that the black hole is in much, much more quantum states than the lighter one. Then the heavier black hole will be favored. It would like to make transitions into those heavier black holes, and you can't have transition backwards. If the heavier black holes would only be in a few quantum states, then it would like to go into one of the more probable states where you have the lighter object plus matter. In other words, the relation between two processes will tell you something about the quantum states the black hole can be in. So this argument can be used to compute how many quantum states can a black hole be in. And now comes the first surprise. We didn't know this. Before, when I gave the argument about things going in and out of the black hole, I was not referring to anything like the quantum states of the black hole. But now, in formulas, the computation is that if you compute the probability that something happens, you have to take the quantum amplitude squared times phase space, the phase space factor. That's the rule. When you teach quantum mechanics or quantum field theory to students, you say, OK, you want to compute whether something happens or not, compute the amplitude, the quantum mechanical amplitude, and multiply that with the phase space factor. But the amplitude may well be a time reversal thing. It's equal for the two processes if you assume time reversal invariance. But phase space is not equal for the two processes, because in one case, it's only the phase space of the final state, not the initial state. In one direction, the final state was a heavier black hole. In another direction, the final state was a lighter black hole plus matter. Ordinary matter allows us to compute phase space. We know exactly how to do that. But we didn't know how to do that for a black hole. Well, now we know, because we can now compare the two different black holes and at least compare the phase space factors between the two of them. And that's a fundamental calculation that doesn't need to be very fancy. And the outcome of the calculation is very surprising and very interesting. The outcome of that calculation is that the number of states the black hole can be in can be characterized as follows. Divide the total area of the horizon into little surface elements. Give each surface element, each little square here, the surface of 0.724 times 10 to the minus 65 square centimeters. You might recognize this is roughly the Planck length squared multiplied by a numerical mathematical constant. So the Planck length square is the size of all the little squares, and then you put zeros and ones any way you like, and the number of ways you can put the zeros and ones there is the total number of states the black hole can be in. This is a simple result of that calculation. Actually, I cheated a little bit. There was one thing you could not compute in the calculation, which is the absolute constant in front. So actually, it could be that every black hole has a number of squares at the side, where you can also put zeros and ones. And we don't know how many there are, but this number is the same for every black hole. No matter how small, no matter how large, this is a constant of integration of the problem. Practical constant. Maybe there are logarithmic corrections, but basically this is a constant. This constant we don't know, but this we do know. And now this makes a black hole look very interesting. It makes us believe that black holes are like elementary particles. You know, in the old days of quantum physics, we used to have so-called Rosenfeld tables. The Rosenfeld tables was a list of all known particles to scientists. And they made long lists of all the particles that had been discovered in all their machines, and all the properties were being listed. And all these particles were given names. Now the claim is, with black holes, we can continue those Rosenfeld tables. We give names to all these black holes, depending on where its zeros and ones are, and so on. So, of course, the name is endless. After a while, you have to give them a symbol rather than a name, but in principle, you can make the Rosenfeld tables. And actually, you could ask now, are black holes elementary particles? Are elementary particles black holes? Are they the same thing? My claim is, quite likely, one merges into the other when you go to the Planck scale. You can not really distinguish anymore whether the thing is a particle or a black hole. In fact, the process of formation of a black hole, when particles fell together, mobile phones here came together to make a black hole, the black hole was formed, and then the black hole decayed by emitting Hawking radiation, and finally the big explosion in the very end. This you could view as a gigantic Feynman diagram, and the Feynman diagram is symmetric on the time reversal. You can read it this way, and you can read it that way. So, and this is just like a very heavy particle. It could be an atomic nucleus, but if it's very much heavier, you could call it a black hole. The distinction between atomic nuclei, very heavy particles, and black holes might be a gradual one and not an absolute distinction. So this is a theory that one should pursue. Now you would think that now we've got all ingredients, all physical and mathematical ingredients, to compute all these properties of this Roosevelt table of black holes, because we thought we had all the physics there. And quite surprisingly, it doesn't work. If you try to do the complete calculation, now make the Roosevelt table, compute all the properties you can of this black hole by just computing everything you know or want to know about this horizon. You discover you can't do it. There's something fundamental missing. And that is that there's something fundamentally wrong with the whole argument. And one thing was already observed by Hawking. You start at any initial state, the black hole you get in the very end looks the same. Not only does it look the same from a classical point of view, even if you apply quantum mechanics, it looks the same. It looks like a light bulb with electric current going through, which emits light, and that light bulb is in a thermal state. And the thermal state means that quantum states are all mixed. And again, in mathematics of quantum mechanics, we make a distinction between pure quantum states and mixed quantum states. And then when you do this calculation, any way you would like to do it using the principles that are just outlined in words, you will get a black hole always in a mixed quantum state. So naturally, physicists then ask, but what if I started with a pure quantum state? Suppose this collapsing star, all these mobile phones, I identified exactly which quantum states these mobile phones were in. Shouldn't I get a black hole in a pure quantum state if you do this? Well, Hawking said no, because I calculated it, it's a mixed state. But then you'd have to assume that pure states evolve into mixed states. And that's not allowed according to ordinary laws of quantum mechanics. And therefore, there's something wrong with the entire argument. What is wrong can again be displayed in graphics rather than in formulas. If this is a black hole formation, now time runs vertically, space runs horizontally, and this is a wave of a particle which sits there at the moment the black hole is actually being formed. Here the horizon opens up. The blue region is the region inside the horizon. And then when you compute what happens to this wave, well, the wave will propagate, but part of the wave will go inside, part of the wave will go out. And now you do quantum field theory, you find that the energy packet of this wave is divided over a region which goes into the horizon and a region that stays out. We call such a thing a quantum entangled state. There's quantum entanglement between the objects going out and the objects that go in. But the objects in are fundamentally unobservable. You can't measure anything that sits inside the black hole. So the observer only has to stick to measurements outside the black hole. Therefore, I can only observe part of the quantum mechanical reality of this configuration. Because of that, the observer doesn't have access to the full quantum information of the black hole, and that is why Hawking found the black hole to be in a mixed quantum state. But he said this is fundamental. You can't do anything about it, so the black hole cannot be in a pure quantum state. This was very, very mysterious, things that we didn't really understand. So this is the words that go with it, but let me continue. Mixture means in thermodynamics that you typically get that the density matrix of the quantum thing is a constant times e to the minus beta h, where h is Hamiltonian. This is if you apply Boltzmann's theory of thermodynamics in a quantum mechanical setting, and you get a sum of an infinite number of states which has a Boltzmann weight factor in here. And that's what we call a quantum mixed state. That's the state that you find the black hole to be in, where beta is the inverse of the temperature of the black hole, which was given by this formula as described by Stephen Hawking. So there's something fundamentally wrong. And now physicists started to fight. We have all these arguments, and there are at least 3 camps of different opinions about how this problem should be solved. One was originally advocated by Hawking. who said, well, this is too bad. Black holes are not like particles. They do not obey a Schrödinger equation. They are entities all by themselves, and they turn pure quantum states into mixed quantum states. Too bad if you don't believe it. But then there are other people who said, no, it can't be quite right. But maybe that information that went into the black hole, all these waves that disappeared into the black hole, will eventually come out when the black hole explodes. The black hole disappears altogether. So everything that went into the black hole should now come back to the open. That would be the remnant theory. The black hole survives eventually as a very tiny grain of matter, which contains everything that anybody ever threw into the black hole. But that is so much that these remnants would represent an infinite number of different quantum states. Those remnants would not obey ordinary laws of quantum physics. Those remnants would be like Boltzmann particles, not fermions, not bosons, but Boltzmanns. And we have never seen any Boltzmanns in ordinary physics, nor do we believe that those particles can exist. They would not obey the ordinary laws of quantum field theory. So there would be still something fundamentally wrong with this idea. So the last position, which I also have defended, is that number 3, there is something wrong in the original derivation. It's not quite that simple. And actually, Hawking radiation already contains all these quantum states. So the particles come out. The quantum information comes out in the form of Hawking radiation. That is just like a light bulb. If you send an electric current through a light bulb, it emits particles. It looks like heat. It looks like thermal particles. But of course, you can imagine a light bulb to be in a pure quantum state. Then, of course, you have to take all those electrons which you send through and make sure you have registered the quantum states they are in. And then the light bulb will be in a pure quantum state. In practice, you won't ever see that. You won't be able to distinguish experimentally a light bulb in a mixed state and a light bulb in a pure state. Similarly, you will not be able to detect experimentally when you ever would see a black hole from close. You will not be able to see whether it would be in a pure state or a mixed state. But that means that from a pure mathematical point of view, it could be in a pure state as disguised with Hawking's radiation. But that would mean that something was wrong with Hawking's argument, and so Hawking wouldn't believe that. But I'd say that black holes require a modification of our derivations. Because if you follow Hawking's argument to the letter, then you get apparently the wrong answer. So something has to be changed in order to get the right answer. You have to modify some of the axioms of quantum gravity. And the big question is how you reconcile that with the notion of locality. You would think that the horizon is a local property. It's like a blanket going around the black hole. The blanket has little hairs and properties that define its behavior at every spot on the blanket. This you would like to have, and this you have to give up when you describe the Hawking radiation as in terms of pure state. So something goes wrong, and I would like to conclude from that there's a paradox in physics. Having such paradoxes is, of course, very important. One just such paradox set Max Planck to think about the statistics of radiation emitted by heated objects. There was something wrong with theory of before 1900 about how heated objects emit radiation. So when he solved the paradox, he found that there must be energy packets, and that gave rise to a complete new domain of physics called quantum mechanics. Now we have a very similar paradox. And my belief is that if we will be able to resolve this paradox, we might discover new domains of physics. So that's why I think this trying to solve the problem is so important. It might force us to think differently about particles and gravity than we usually do. So now, remarkably, people who do string theory also arrived at the same conclusions I did, which is that black holes are in a finite number of quantum states. They preserve purity in quantum mechanics, so they behave exactly the way I described it. Then you find that there's an infinity of particles close to the horizon. Too many to be able to handle, so we have to remove many of them. And that's the brick wall theory. So whatever you do at the horizon of the black hole, you have to make a brick wall with a thickness of roughly a Planck length thickness. And then all this infinity of particles disappear, and then you get something that looks much more decent. But how exactly to describe that brick wall is something of a big mystery. I think I should have to skip a few arguments. I just want to say that the way to reach that situation is as follows. you can consider a particle going into the black hole. As seen by a distant observer, the particle never enters the horizon. As seen by that same distant observer, the Hawking particles come from time equals minus infinity, and these particles cross each other somewhere. Where they cross, they should interact. At first instance, you ignore that interaction. You say you apply linearity. In first approximation, particles just go through each other without any effect. That cannot be right. And the reason is that if you compute the center of mass energy of these particles, you get horrendous answers. You get many times the mass of the entire universe if you sit very close to the horizon. That means that the gravitational interaction will be tremendous, and they will form black holes all by themselves at this spot. So there must be something fundamentally wrong in the assumption these particles don't interact at all at this spot. No, they interact extremely strongly gravitationally. And I'll skip this part. This is what I wanted to show. The particle goes into the black hole, and then here are the particles which are sitting at the horizon, either queuing to go in or queuing to come out. But the particle is sent into the black hole has a gravitational effect. And this is the gravitational effect. There's a dragging effect, which you can compute exactly because it's a classical calculation. But you find that the dragging effect causes the ingoing particle to have an effect on the outgoing things. And this is how I believe that the ingoing information is being transported back into the outgoing particles by this dragging effect. You can compute the effect, and then you get a very interesting result, which is that black holes and white holes are the same thing. I didn't tell you yet what white holes are. A white hole is simply the time reverse of a black hole. Astronomers also always ask themselves, if you can make a black hole, suppose by having things collapse and so on, suppose somebody makes a movie of a black hole being formed, and now turns the movie backwards in time and shows what happens backwards in time. Laws of nature, we thought, are time reversal invariant. So if you can have the formation of a black hole, couldn't you have the evaporation of a black hole or the explosion of a black hole, but just time reversing the formation process? And now we say, yes, you can, but the most probable things that come out of a black hole is just Hawking radiation. So yes, the alarm clock could come into the black hole, it could also come out, but its probability of coming out is just controlled by the Boltzmann factor, which is very, very small for macroscopic objects. But doing that, yes, you can compute that a black hole can actually also decay by emitting the stars that just made them. Just the probability is very small. Mathematically speaking, we say a white hole and a black hole are quantum superpositions. That is to say, if you take all possible black holes in a certain quantum superposition, you get a white hole. If you take all possible white holes in a quantum superposition, you get a black hole. So the relation between black holes and white holes, and that's an important thing to remember, is just like the relation between a particle in position space and a particle in momentum space. So one is a superposition of all the others. And that was a very important piece of insight which came from these kind of calculations. So the picture we want to arrive at is as follows. We want to understand that nature consists of singular particles. There could be bound states of particles here. There could be little black holes, but there could also be very large black holes. And now if you consider a very large black hole, you have to describe its horizon as if it were a flat space which has vacuum fluctuations containing all these. So we want to have a consistent theory of nature built along these lines, but this argument is a circular one. Before you can understand the horizon of a black hole, you have to understand small black holes as well as these particles. But before you understand small black holes, you have to understand how the horizon behaves. So our problem is a circular one. And the big difficulty that we have in theoretical physics is how to get into this spiral and how to make a theory that bites itself back into its tail in a consistent manner. This is very difficult. It requires lots of intuition and smart ideas. And I think that an entire future generation of physicists will be needed to figure out how this all should be done properly. I'm over my time, so I should stop at this point. Thank you very much.